Okay, so I'm going to talk about smart records, which is basically part of the larger theme of composable routing. And the status of this project is that we have actually an end-to-end V0 committed and it's working, but we're not just at the point where you guys can start dog fooding it. It's coming soon, probably a couple of weeks or so. First things, I just want to give you a broader view how this fits in the larger composable routing picture. So composable routing is this effort which Juan alluded to, essentially trying to make all the parts of the end-to-end content routing very reusable with each other, so composable, which basically means making them individually generic. Smart records are the data sort of half of the composable routing, and the other half is the logic of composable routing. So we're going to focus on smart records here. Just for your context, though, so what is this routing behavior that I'm referring to? This is the other side of composable routing. It basically includes three things, which are how you write links that point to content, so sort of rich links, not just CIDs, which are just opaque and have no hints in them. So how do you write links? How do you define how do you describe context at every given peer? Because every peer has their own circumstances where they live in the network, and this is their context. So how do you describe it? And how do you, context also includes the preferences that peers have when they want to do a routing of links. And finally, routing logic is given a link and a context, how do you actually perform finding a piece of content? So routing logic, the thing that makes this a framework is that routing logic, in other words, what you end up doing to actually find the content, is a function of the link, the context, and the records. And the function is fixed, which is what makes it a framework. We're just going to talk about smart records today. Okay. So roughly, so what are they? The abstract way of saying, sort of like the very general way of saying what problem they're solving, is essentially to say that they're trying to sort of create a standardized shared public medium for writing and reading by multiple participants, which are talking to each other using multiple protocols. And the actual location of this public medium is scattered on multiple locations. So now this is a mouthful and it sounds fairly generic. So putting some flesh to it is just reinterpreting this statement in the context of the familiar DHT that we currently have. So what's happening in the DHT right now is that we have the DHT actually does the DHT protocol, like literally in the IPFS stack, it actually takes care of two jobs at once. One is that it sort of finds peers for you at a given key location. And then it also happens to be implementing the put and get operations, which are currently very hard coded to do a very specific type of data storage. So the first thing that we're saying here is that the putting and getting of data should be decoupled from the DHT. The DHT should only be doing finding of peers. So that's sort of step one. Whereas the functionality of actually storing data shared by multiple protocols is this new project that we're discussing now called like Smart Records. And it should be a separate protocol that just happens to run side by side on every IPFS node together with the DHT. Of course, smart records are generalizing the put and get functionality in that now you can actually write any data type, not just the hard-coded ones that are currently used for provider records and peer records. The thing to note, though, is that we also want to make this whole notion of a smart record sort of a self-contained entity, if you will, that is also portable. And why do we want that? Because this kind of a shared data space does not only necessarily live in the DHT, which is the most obvious motivating example, but you could also imagine sort of sending these records across completely different kinds of protocols. And in fact, currently even in this session, but also in W3D work group, people are already trying to send records through PubSub and other protocols. So if smart records, which is the standard that wraps data, is something that is self-contained and isolated from other context, you could compose it, in other words, reuse it in different settings, whether it's with a DHT or with a PubSub or any other sort of exotic combination of protocols. What is it exactly? So these are sort of problem statements in a way so far. What is it exactly? Well, the sort of like the simplistic way of saying it is it's basically kind of like upgrading our DHT values to become publicly writable, publicly updatable JSON documents. Of course, it's actually much more than that, but this is a good description at high level. It's another way of viewing it is as a mixture of a CRDT, and I'm going to unpack this in the next slides, and smart contracts. The key point here is that the data associated with the record, we want to view it as a replicated state machine, which has its own interface and virtual machine. So hence it's portable. And the key requirements, so the key benefits that we're going to get from it is that it supports, like I said, reading, writing, merging, and some smart services that I'll mention at the end. Now, I want to talk next about the use cases that it immediately enables. The first thing is it enables the deployment of new applications to the IPFS network without upgrading the network. So if somebody writes a chat application, for example, where the participants want to exchange chat-specific data, they can store this in the DHT, because the DHT now will allow you to kind of use your custom data structures, not just the hard-baked ones. It's also another design goal here is to enable different protocols to interact with each other. That's why records are a public blackboard where it's one blackboard. So there's one document per key where multiple protocols can write to it in sort of their own spaces. And therefore they are able to sort of read each other's data if they understand it and sort of benefit each other, something that's not really possible today. Some other use cases are, they also might end up being useful for facilitating cryptographic protocols that require a third party. And I say trusted in quotes because depending on the setting, you may or may not trust a DHT node to be a fair sort of judge between two other nodes, but it has the potential to be used in this case as well as some kind of an opportunistic judge, which enables lots of cryptographic protocols. I've only listed fair exchange here. And generally speaking, something that I'm very excited about, sort of a side benefit, is it actually unlocks application development on the DHT to the public, kind of unconditionally. And this can produce lots of interesting outcomes. It should when we release it. So let me get to the technical aspect of this thing, and basically kind of discuss our thought process approach, sort of leading to the design that we currently have. So the key thing to just remember, this is just sort of use the DHT as your mental model. The key thing is that there are multiple hosts of the data that is being stored for a key. You know this because this is how the DHT works. So there are multiple writers. So many people, for instance, write provider records for the same key, and there are multiple readers because many people might be interested in the same key. So the players are multiple of each. And these are the hard technical requirements that this shared medium has to have. So first of all, the data model is generic has to be generic because we want different protocols to be able to use it. So think JSON or IPOD. In fact, they're the same thing. So the IPOD data model is the same thing as JSON. So the data model is JSON, roughly, sort of bottom line. The updates to these records have to be commutative. This is simply because the whole system is asynchronous, so any two updates can be reordered, and the semantics of what's happened shouldn't change. The values, so these JSON values that are attached to keys, have to support merging, because that's because the value of a record is virtually always distributed across a few different DHT nodes in the DHT setting. And so reconstructing the record really involves collecting all of them and merging them together. So merging has to be supported. And merging must commute with updating for the same reason, asynchrony. And the final, and this is the sort of like the crux one, is that conflicts, which can only happen during merging and updating, must always be resolvable, because that's a public medium. They always have to be resolvable, right? So, and this is designing this part is sort of like what I want to spend a few slides later on. Now, another aspect I want to point out is that it is pretty clear that sort of a public medium like this requires regulation, meaning what I mean. So regulation generally, but specifically the most natural kind of regulation is to say anytime somebody is updating a piece of the record, we would expect that we can impose payments for different kind of aspects of the operation. Payments per size, so how much data you write, payments perhaps for how long you want what you've written to stick to the record, and you could sort of envision other kinds of payments. But the reason why assuming that payments, or at least some virtual form of payments, are part of the system is kind of like seems like a straightforward sort of thing to assume, is because it's pretty clear that if you can just publicly write, if you can write a public blackboard for free, there are no sort of well-behaved ways of preventing denial of service attacks other than payments. Anything else would essentially be compromising with the clean semantics of the product itself, of like writing to this document. I know some folks are going to be sort of concerned about, well, how are we going to use this technology in the IPFS setting where there are no payments at the moment? It's not a problem in the sense that you could use these records without a payment scheme and just reuse the techniques for denial of service that are currently, these are really heuristics for denial of service, which are currently being used in IPFS. So I'm not gonna delve into this. And next, so I wanna talk about so this is how did we sort of design how to do conflict resolution and really kind of like the semantic aspect of this service. So first, stepping back for a second, there's two extreme ways you can approach conflict resolution in general. So one is the destructive approach, in which case you essentially define some form of competition between different writers to a location in the document, and the winner gets to override the loser. Competition can mean lots of different things. It could mean, I mean, it's up to you. It could mean maybe people are like bidding money for who gets to write somewhere. Maybe it's based on who comes first, or maybe it's based on some rules that you can embed in the document itself. You can get very creative with how you define competition. And that's also the reason why it doesn't seem to be the right way to go if you want to be general, because there's too many different sort of possible designs here. In the alternative extreme is to use non-destructive conflict resolution, which basically means essentially remember all updates as they are and don't try to sort of merge all the updates into a single document, and just communicate all the updates to whoever wants to read the document. This has its downsides. It takes a lot of space, but also it's very difficult for, what's more concerning to me is it's very difficult for our users, which is application developers, so users of smart records, to actually deal with a data structure that is a sequence of updates, because they have to worry about sort of reconciling them and merging them themselves, and that's developer friction, which I like to avoid. I think it's pretty key to avoid it, especially given that we're like giving this to a wider audience. The good news is that there's a middle ground, which gets actually the best of both worlds. So the middle ground is simply to allow, so to basically keep a separate copy for every writer, so a separate copy of the record for every writer, and this makes sure that writers cannot DOS each other, so they cannot write over other writers' data. But when they update their own records, they can overwrite to gain efficiency. And the pros and cons of the middle approach. So first of all, the good news is that if you have the middle approach as your basic API, you can implement any of the other approaches, like the competition-based, for instance. You can implement it at the application layer. Now, one downside is that slightly more data resides on the record host, because you have a copy of the document for every writer. Of course, you only have a copy of what they have written to the document. I think this is a fair price to pay, also considering the fact that if you believe in having a payment model for all the rights, the host of the records not only doesn't mind people writing a lot, in fact, they probably prefer that in order to make money. And of course, on the other hand, the middle ground approach actually uses considerably less data than the extreme non-destructive approach. Okay, so and now let's, having kind of given you our thinking behind the conflict resolution, so what is really the sort of like the product looking like? What's the model? So every peer identified by a public key writes to a peer-specific document for any given key. I already said these peers can overwrite their own documents, and the last piece is that every time a peer writes sort of updates a piece of the document, they get to specify a TTL for every single node in the document that they write. This of course is obviously to accommodate protocols that have different temporal semantics of how they want the data to stay. The actual interface of the product, so what sort of application developer gets to interact with, is really just putting what we have so far into words. Peers update a key with a change in the value that they want to update, and they get to specify duration for each node in this value, and they also get to set what is the sequence number from the writer's point of view of this update, and I'm going to mention in a second why this is necessary. And retrieval works like this. You just say, I want to retrieve all the values for a given key, and you end up getting a list of values, one for each peer that has written to this key. These things, by the way, are easily mergeable from a developer point of view, unlike getting a list of updates, because each individual peer's record should be a semantically correct document with respect to the protocol. That's not true if you were sending individual updates to the reader. Why do we need to send the peer sequence number? Because when two different DHT nodes try to merge the documents they have for the same peer, knowing the sequence numbers from the point of view of the writing peer makes the merging possible in a predictable way. one addition that will happen in the near future to the retrieval part of the interface is that we're not going to allow a retrieval of all values, because eventually when this system starts to get used heavily, you're going to have quite a lot of data in a single record, perhaps pertaining to different protocols, and it might be too much data to retrieve if you only care for one of these protocols. So we would change the get all with give a selector and get back only the schema, the subschema of the record that you understand. The final thing, which I didn't want to emphasize too much in this talk, because I think there's kind of already enough new concepts to kind of absorb. But the final thing is that these records that people get to write can have sections of them that have a special meaning to the record hosts, and in particular, they're essentially ways of asking the record host to perform some service for you, some service that goes beyond just writing the data to the record. And so examples of services like these are, for instance, making sure that the multi-address is properly formatted and also reachable before you actually write it to the peer record. That concludes my talk.